What can gravitational waves tell us about the universe that light can't? Is there any update on the search for Planet 9? And is there any such thing as the present, or is everything in the past? All this and more in this week's question show. It's time for the question show. Your questions, my answers. As always, wherever you are across my channel, if a question pops in your brain, just write it down. I will gather a bunch of them up and I will answer them here. Now, this is just a part of the question show. We also do this live every Monday at 5 p.m. Pacific time. So if you want to have your question answered live, come join the show. It's a lot of fun. All right, let's get into the questions. Love metal rocks. What can gravitational wave astronomy tell us about the universe that light can't, given that both light and gravitational waves travel at the same speed? What are some examples of things that we expect to find out? So astronomers have known about the presence of gravitational waves now for a few years. Like LIGO finally came online, detected its first colliding black holes, and we got this direct observational evidence that gravitational waves exist, as predicted by Einstein. Correct again, but to be able to actually measure them. And then LIGO had a bunch of refits and came back online and was even more powerful. And just in the last couple of weeks, LIGO has come back online once again to do more observations, now being able to reach about twice as far, to be able to detect more sensitive collisions between various exotic objects. And so we should find out about multiple gravitational wave events every single week. In fact, they're going to happen so often now they'll just be routine, and it'll just be the special events that are happening. But theoretically, like, what can we use gravitational waves for that maybe we can't use regular electromagnetic radiation astronomy for? And, you know, we talk about this idea of multi-messenger astronomy, that you've got light, electromagnetic radiation, and that can be radio through visible light, through X-rays, gamma rays. But then we also now have gravitational waves, which are a completely different form of transmission of information. And then like the third one might be neutrinos. So we're getting to this place where we've got multiple ways to see the same event happening. And so there's a couple of advantages for gravitational waves, and like, they have huge disadvantages. The biggest one being that they are incredibly weak. Like, when any time mass is moving around, it's emitting gravitational waves. Like, you're walking around, you wave to your friends, you're throwing gravitational waves at them, but they can't see it. They can see the light being reflected off of your hand, no problem, but they can't see the gravitational waves. And so it's only the most extreme events that we could see. When you've got black holes with dozens of times the mass of the sun crashing into each other, only then do we get this tiny detection of a gravitational wave. So the first thing is that gravitational waves will pass through things that are obscured by matter. And so when you think about, say, a supernova, when the supernova goes off, you've got inside the envelope of the star, you've got these layers that are crashing down inside, and then you've got the black hole forming, and you've got the outermost layers bounce out and then ripple off out into space. And in fact, when we observe a supernova going off, we will actually detect the neutrinos before the light coming from the supernova. And neutrinos move slower than the speed of light, and yet we see them first because they're able to escape through the material of the star, while the radiation has to sort of make its way out through all of the layers of the star to finally escape out into space and then move the speed of light. Well, gravitational waves are going to be moving at the speed of light, but they'll be able to pass right through the star. And so theoretically, if we were watching a star that we knew was going to go supernova, we knew it had like some kind of unbalance where when it exploded as a supernova, it would give off like some kind of quick wobble in space. And theoretically, LIGO can do this. Then you would see the gravitational waves first, and then you would see the neutrinos come by, and then you would see the light. And so in theory, if we had like a really well-tuned gravitational wave astronomy system, you would have this early warning. You would see the gravitational waves from a supernova. Astronomers would go, oh, there's going to be a supernova in that star over there. Quick, let's observe the star. And then a minute later, they actually get a chance to see the supernova. So like that would be amazing. Of course, we always talk about the early universe before the cosmic microwave background radiation. So like the first 380,000 years of the universe are obscured because light couldn't escape out into the universe. Even though it was there, it was trapped inside what was the early universe. Well, gravitational waves could pass through that. And so we could look right back to the very beginning times of the universe. In theory, there are primordial gravitational waves that were released during the Big Bang, and they are moving out in the universe. They're all around us all the time, like the CMB is around us all the time, and they would allow us to see just nanoseconds after the Big Bang itself. And so just imagine all of the answers that you could get by being able to measure into the early universe. And then the last thing that I can think of off the top of my head that gravitational waves are going to be really useful for is measuring the expansion rate of the universe, because they provide a truly independent way of measuring the universe. I'm not going to go into all the details, but the gist is that, you know, if you detect two black holes colliding with each other, the mass of the two black holes, as well as how long it takes for them to come together, releases the gravitational waves out into the universe. And in fact, it's the velocity of the two black holes that gets converted into the gravitational waves that spread out into the universe. And astronomers call this the chirp mass. I'm not sure why they do, but I guess because they see this chirp of gravitational waves in their sensors. And so then if you also know the optical counterpoint of that, and that's like what the kilonova event was back in 2017, you could see the gravitational wave signal. You also can see the electromagnetic radiation. If you know the galaxy that the event happened in, you get an independent measurement of the expansion rate of the universe. You can essentially measure how fast the galaxy is moving away from you because of the gravitational waves. You get some pieces from the electromagnetic part of the explosion, and you can calculate the rest based on the gravitational waves. And so suddenly, when you are detecting multiple gravitational wave events every week, you're able to start really mapping out the expansion rate of the universe. And the farther you go in being able to measure out gravitational waves, the more you can put out this bubble of certainty about the expansion rate of the universe. And so if we can go to 1 billion years, 2 billion years, we're measuring very accurately the expansion rate of the universe. And hopefully eventually someday we'll get all the way out to the very edge of the observable universe and get like a really good measurement for the expansion rate, and maybe finally solve the crisis in cosmology and really know how fast the universe was expanding at different times along its evolution. At this point, you've probably noticed the Star Wars planet that appeared above my shoulder, and this is a way for you to vote for the question or answer or combination that you thought was the best. So just go ahead and watch all the questions, all of them, and then in the comments down below, as you are typing your own question, just briefly mention the Star Wars planet that you enjoyed the most, and then we will count them up and we will celebrate them here. So last week, we had Yes, That Kareem talking about both SpaceX and Blue Origin refueling space in microgravity. And then I talked about how excited I was for space refueling. So congratulations to Yes, That Kareem. Glad everybody liked your question and my answer. So again, don't forget to vote at the end of this week. It's time for the book club. And I mentioned last week that I am reading through the Culture series, and I know that I have a responsibility to get through these books as quickly as humanly possible so that we can move on to different series. This is, of course, the problem. When someone gives me a series to read, I kind of want to read the whole series. So this week, I read the next 3 books in the series. So I read State of the Art, which is a collection of short stories, mostly about the culture interacting with various groups in the universe. I read Accession, which is about what happens when the culture meets a civilization that is more powerful than it, and you know, it's been able to spend all this time I guess being magnanimous, and now it has to resort to dirty tricks to get ahead, and also you get some perspectives of some truly alien species in it. And so far, this has been my favorite. Like, a lot of people really like the use of weapons, but Accession has been my favorite book in this series so far. And the one I'm reading right now is called Inversions, which is about a sort of, I guess, how the culture interacts with civilizations that are less technologically advanced, and the different philosophies in how do you interact with, you know, if they don't have the same kind of technology and maybe different kinds of morals, and you want to try and influence them without ruining their civilization. What's the best way to go about that? And they sort of explore this in the book. So hopefully within the next couple of weeks, I will have finished the entire Culture series by Ian M. Banks, and then I will move on. But boy, I'm so grateful to be reading this series. So thank you everybody who has been recommending it to me for a long time. And I highly recommend follow in my footsteps, read the Culture books by Ian M. Banks. You know, there are SpaceX drone ships named after them. They are foundational, like the Foundation series. But we'll have a link to the book club down in the show notes down below, and you can go ahead and just recommend books to me in the book club. And the way this works is you recommend books, I read them, and I tell you what I thought. So definitely I'm going to run out of books soon. Help! Parashar Siddharth. If the Big Bang happened 13.8 billion years ago, how come we see 46 billion light years away on each side? Like, when I first started to do this, I didn't really understand exactly sort of how the size of the universe worked, and I made some pretty fundamental mistakes that people slapped my wrists and helped me understand much better. And you have to use terminology very carefully, and in fact, I will often intervene with my writers on Universe Today if they aren't expressing this properly, because, you know, it's kind of tricky. So when we see a galaxy, say in a picture from JWST, and we can calculate that the light has been traveling from that galaxy for 13 billion years. And we know that we are seeing that galaxy as it looked 800 million years after the Big Bang. That galaxy is not 13 billion light years away. It's only that the light has been traveling for 13 billion years, but the universe has been expanding and the galaxies have been moving and we have been moving. And so you get the actual distance to that galaxy, if it's like, or the actual distance of the cosmic microwave background radiation, for example, is that 42 billion light years. And what you do is essentially, if you add up all of the expansion of all of the parts of the universe between you and that target that you're looking at, that's when you get that full distance to get there. It's some neat ideas. So yeah, like if the universe was not expanding at all, then an object, if you saw an object that was 13 billion years ago, then it would be 13 billion light years away. But the universe is expanding. And there's an interesting thing, like without dark energy in the universe, those things that we see right at the edge of the observable universe, they would only be 41 billion light years away. It's that dark energy has already contributed about 5 billion light years to that distance. And so, in fact, we see them at 46 billion light years away. So, like, I know it's hard to wrap your mind around this, and yet it's a sort of minefield of ways to say it wrong. And so you'll hear me very carefully say, we are seeing this galaxy as it looked 13 billion years ago. The light has been traveling from this galaxy for 13 billion years. We are seeing it as it looked just 800 million years after the Big Bang. And, you know, being accurate about this kind of thing is important. So I hope that helps. Kuti 007. Is there no present? Do we live in the past as calculated by an event plus the speed of light? Even a thought is delayed? Yeah, you could say that we live in the past at all times. You know, when you get, I don't know, if you get shocked on your fingers, you know, it can take several milliseconds to reach your brain. Apparently, the fastest the brain can react to stimuli is about 1/20th of a second. And so everything that you see out there is delayed by some number of milliseconds, depending on, you know, it's a good thing that the eyes are so close to the brain because it minimizes the lag in between. But you know, when you are looking at your computer screen, the light is taking a couple of nanoseconds to get from the screen to your eyeballs, and then a few more milliseconds to get from your eyeballs into your brain. And so everything is delayed. And then when you are seeing things that are at the edge of the horizon, maybe it's taking tens of nanoseconds. And when you're seeing the moon, you're seeing as it looked like a second ago. And when you see the sun, it's 8 minutes ago. And when you see Alpha Centauri, it's 4 years ago. And when you see Andromeda in the sky, it's 1.5 million or 2 million years ago. And it just goes on and on, right out to the edge of the observable universe, as we said, 13.8 billion years ago. And so there's like an interesting idea about this. Like in the book Accelerando by Charles Stross, he proposes that it's this speed of thought for technological civilizations that defines the limit for how big they choose to get. With the speed of light being the limit, there's no real value to have a civilization that is larger than, say, about the size of the Earth. And they call this like a Jupiter brain or a Matryoshka brain. You've got this sphere made of computronium that is computing, and it's sending signals back and forth. And once you get beyond a certain size, the lag just gets ridiculous, and you just don't want to be a part of that civilization anymore. You might as well be part of a completely different civilization when you are at another star system. Like the lag to travel 4 light years for you to send signals back and forth through your galactic empire is just, it's too much. And so future civilizations just will only choose to live in their home system because that's where the lag is low. And I'm not sure whether I buy it, but it's a great explanation for the Fermi paradox. And so if you haven't already read the book, Accelerando by Charles Stross sort of goes into this. So I highly recommend it. Recommended as part of a previous book club. Mark Scales. Hey Fraser, is there any update on the search for Planet 9 in the solar system? And do you think it actually exists? So there are no real updates to the search for Planet 9. You know, the idea of this Planet 9 was based on research by Mark Brown and Konstantin Batygin a couple of years ago, where they were measuring the movements of various objects in the Kuiper Belt. And they found that you could only explain the weird clustering that they saw if there was a more massive object out in the Kuiper Belt that is influencing them. And we have certain constraints, like we know the maximum size this could be because of the WISE survey. This is a space telescope by NASA, an infrared telescope that scanned the outer solar system looking for large, cool objects. Like, do we have a brown dwarf companion to the sun? And the answer is no. And so they're able to constrain down the size of the objects that could be out there, but you could definitely have a Uranus-Neptune-sized object that is orbiting within the Kuiper Belt, or an Earth-sized object that's closer, and they would be beyond the limit of what the WISE telescope could have found, and yet they could still be out there. And so at this point, nobody has found this object that is influencing them. Searches have been made, but nobody's been able to turn it up. And so it really feels like we're waiting on the Vera Rubin Observatory, which is going to come online later on this year. It's going to be doing full scans of the entire southern hemisphere every few days. It will detect any object moving in this region to ridiculously faint magnitudes. Like, it's going to find all the asteroids, all the comets, all the supernova, and in theory, it's going to be the machine that's going to find Planet 9. So don't anticipate any updates on Planet 9 until the Vera Rubin telescope comes online and data has been gathered, and then either someone's going to go, oh, there it is, right? And they're going to do follow-on observations with JWST, or it's going to go weeks and months and years and nobody's going to be able to find it. And then they're going to have to go back to the drawing board to try and figure out, why are these objects clustering out there in the Kuiper Belt? If you like my answers to your questions, as well as the other things that we do at Universe Today, consider joining our Patreon club. This allows us to keep a minimum ads for everybody. And as a patron, you will get an ad-free experience on universetoday.com for life, even if you unsubscribe. You'll get ad-free videos, early access to interviews, as well as other perks that are exclusive to our Patreon community. Thanks to everyone who has already subscribed, and welcome to the recent newcomers: Just Paul Davis, Gert Control, Trevor Rittmiller, E. Brent Hall, Michael Kizelinski, Henry Whitehead, Frank Malafant, Josh W., Wael Al-Rifai, Void, Tomas Weiser. Join the club at patreon.com/universe today. Starman67. As our solar system formed from the same nebula, there would be great chances that some of the rare elements found here would also be found on Mars. Wouldn't the Tharsis region be a great place to mine? So with the larger planets, the more massive planets like the Earth, Mercury, Venus, Mars, you had them separate out into the lighter elements on the surface, and then the heavier elements would sink down inside the planet. And so all of the really interesting heavy elements that are present in the solar system, in the periodic table of elements, they're underneath your feet. They were gathered together as part of the Earth, and then they sunk down into the planet. Now, we do still see deposits of iron and other elements. In some cases, they're left over from meteorite strikes that hit the surface of the Earth. But the vast majority of the precious, heavier elements are thousands of kilometers beneath our feet. Mars is less massive, and so it probably didn't form into layers as well as the Earth did. But really, the best places to find these elements are in the asteroids. In the asteroids, they didn't layer at all. You could go to a fairly interesting asteroid and you could find deposits of gold and silver and platinum and iridium and all of these things just sitting around on the surface of the asteroid, waiting to be picked up and stuck in a bag by a hardy asteroid miner. So really, I mean, Mars would be fine, but like Mars would be really tough to try and land on, go into the gravity well, mine from there. No, you want to go to the asteroids. That's where all of the interesting material is going to be found. Samuel Doak, is there enough water on the moon to sustain a permanent colony? Depends on what you mean by a permanent colony, but yes, like if you go to the permanently shadowed craters at the south pole of the moon, the place where water ice has been seen from space, has been blasted out of the surface with the L-Cross mission, we know that there is vast reserves of water there. It's tricky to get to because it is in the shadow, and so you need to figure out a way to get some kind of mining equipment that is solar powered or maybe nuclear powered into the shadowed crater, down the side of the crater, gather up the water. Are you chip it away? Do you haul it by big lunar trucks, bring it back to your station? But yes, in theory, like it's all there and it would last for a long, long time for a reasonably sized station. The oxygen that you need is present everywhere on the surface of the moon. Like you just have to crunch any rock and it will release oxygen with the right heating. And in fact, there is water just present in every cubic meter of lunar regolith across the surface of the entire moon. You just have to be willing to heat up like 1 cubic meter of lunar regolith to give you 1 water bottle's worth of water. But theoretically, it's worth doing if we want to sustain a lunar colony. But it's always going to be expensive and it's always going to be complicated. Like we're not going to have this wonderful city on the moon for a long, long time until our technology has advanced to the point that we can trivialize our existence on the moon. Mitchell Altschuler, could we use other stars besides ours as a gravitational lens? And if yes, what are the downsides besides using a star farther away, which I assume would have some limitations? So you're basing this idea on the concept of the solar gravitational lens, which we've talked about quite a bit. And I've got an interview with Dr. Slava Turshev about the solar gravitational lens, and then a follow-on interview with him about how to get out to the solar gravitational lens. So it's a fascinating idea that the sun will act as a natural lens. And if you can get out to about 650 astronomical units away from the sun and then just keep traveling outward, then you will be able to see exoplanets with a resolution of like 1 megapixel. Would be amazing. But the key is that you need to align the sun and your spacecraft and the target perfectly. There is this observation cone that is moving away from the star. It's like a tunnel that you need to keep your spacecraft perfectly oriented inside this cone. And it'll go on forever as long as you stay perfectly aligned. And actually, the farther you get from the sun, the better the lens becomes for you, because the sun becomes less and less of a blob of light in your image, and you get more and more of the image around it. But the key is that you have to keep this aligned perfectly across 1,000 astronomical units. Like if you're off by a nanometer, things aren't lined up. And so finding a star that is going to be perfectly between us and something that we want to look at will happen from time to time, but it's not going to remain lined up. We're moving, the star's moving, the target's moving, and within minutes, things don't work. And in fact, astronomers detect planets using gravitational lenses all the time. You look out into space, you look at all the stars out there, and every now and then one of the stars brightens because some object is passing in front of it, or we're seeing some star for the first time because the star was normally hidden, but now another star is passing in front of it. The two line up perfectly. You get a gravitational lens. And in fact, planets are found because as the two stars move in front of each other, you get the lens kind of warping and wobbling, and you can detect the existence of the planets around the star as they contribute to the lensing effect, and then the star moves away, and then you've lost the lens. And so you can detect the planet, but the downside is that you can never make any follow-on observations. It's a one-time detection of a planet, but some of the faintest, smallest planets that have ever been seen have been done using this gravitational lens method. So the gravitational lens only works when you can perfectly control the position of the star, the position of the spacecraft, and the position of the target. And we can only do that by launching a spacecraft from Earth using the sun as a gravitational lens. Nathan Way, what are the chances of a strange isotope and rare mineral created by supernova? Supernovae are the most extreme events in the universe. Like, they are the mass of a star, many times the mass of the sun, coming together in a moment, creating a black hole. The energies involved here are extreme, and yet this is how particle accelerators work. Like, we take a stream of protons, we smash them at some heavy element, and we try to mash additional protons onto that element to create heavier elements. And when you look at the periodic table of elements, like, all the heaviest stuff was created in particle accelerators, and they only exist for moments until they are unstable and they break apart. And so you could theorize that there are elements out there in the universe created in supernova that are thousands of protons, tens of thousands of protons, like really big elements are created for a moment, but then they fall apart. They are unstable. And we know that they're unstable because we don't find them. Like, every element that we have here on Earth was created by the death of a star, except for hydrogen. But everything else was created through the death of a star. So we know that gold is stable. We know that iron is stable. We know these things are stable and they last for long periods of time. And there are other things that we know decay: uranium, other elements higher on the periodic table. So yeah, in supernova, they are creating the heaviest possible elements, but we also know that they are falling apart immediately. People wonder, like, are we eventually going to find some island of stability where there are more elements higher up on the periodic table of elements? But if there were, then we would find them because supernova would create them. And we can't do anything close. We can't hold a candle to a supernova. And so what exists out there, we can safely assume is what's stable. Richard Price, what space-related film annoyed you the most regarding its portrayal of physics? If you can get annoyed by the portrayal of physics in a science fiction movie, then it is just a target-rich environment, and you will just be grumpy and sad all the time. So the part of my brain that is critical of portrayals of space and astronomy, I just set it aside. I turn that part of my brain off and go, yeah, you get in that warp drive spacecraft and fly across the universe and catch falling people with your robot arms and have artificial gravity and everybody speaks the same language. And I just don't care. Like, tell me a good story. And that's all I really care about. There are definitely some shows that do a great job, and so that part kicks in again. Like when I watched The Martian, was it last week? Someone was like saying, oh, you should watch The Martian. And so we just did. Oh no, that's right. I did an interview with Jean-Michel Gaultier, which will come out on the channel in a few days. And I was we were getting hyped about The Martian. I went and watched it again. Totally holds up. There's a bunch of problems, but you are willing to overlook them because it's so accurate. Or you watch For All Mankind, and it's just so great. It's so accurate that then when there are hiccups, you kind of go, oh, you're 99% of the way there. But for most science fiction that I watch, I just shut that part of my brain off. It has no place. It cannot help me enjoy or not enjoy Avatar: The Way of Water. It is not welcome here. Jesus Solus. Do gas giants have a molten core and layers of rock like the Earth? Yeah, it's believed that at the center of Jupiter, there are many times the mass of Earth in just pure Earth stuff. So you've got rock and metal down at the core of Jupiter, and then that's surrounded by an enormous volume of hydrogen and helium. And then you've got this at different levels of density. And so at the very near the core, you've got metallic hydrogen, and then you've got hydrogen that's acting like ice. And there's all kinds of different layers inside Jupiter. And the farthest outside, you've got the atmosphere, which you've got ammonia and methane and other gases in the outer layer of Jupiter. And in fact, you've got something similar inside the sun. Like, people always worry, like, oh no, what if we crash uranium into the sun? The sun has dozens of times the mass of the Earth in rock and metal and radioactive elements and all kinds of stuff inside of it. The vast majority of the material, the rocky material in the solar system, is down inside the sun. So if you need more of it, you're going to have to dig for it. Jerome, what would you do if you met aliens? Like, when we think about the search for UFOs, we think about how people are skeptical of the evidence that has been provided by people who have made observations about UFOs. It's anecdotal evidence. Like, I was flying in an airplane and I looked out the window and I saw something moving that I couldn't understand. And then I came back and I reported it and it's unexplained. We don't know what it was. Or I was abducted, or I was at work and I looked up and I saw this thing fly by and it moved too fast and it moved strangely that I don't understand. So you've got this eyewitness testimony, but you don't have good evidence. And so, like, if I met aliens and I wanted to prove to people that I met aliens, I would be thinking hard about how am I going to gather evidence about this interaction that would be accepted by my skeptical colleagues, right? Like, what would they need to see? And when you think in this modern age with deep fakes, with artificial intelligence, with Photoshop, with our ability to make things, it would be really tricky to create something that, or, you know, ask the aliens for an interview. I guess I would ask the aliens for some piece of information about the universe, some piece of knowledge that would make a very specific prediction. They'd say, oh, well, if you just open your eyes and close your eyes 1,000 times when you have your back to the moon, you will see the entire universe change color from black to pink. And you're like, huh, okay. And you do this 1,000 times and you look and suddenly the universe, you know, the night sky turns pink. And then you do it 1,000 times more and it goes back to black. And so you could tell other people, like, whoa, I met aliens and they told me this thing about the universe, and everybody tested out and they agree that yes, indeed, this is true. And there's a little bit of this. If you read the 3-Body Problem book in the first one, the aliens prove that they're real by adding a signal into the cosmic microwave background radiation that is seen independently by different observers. And so everyone can be sure that this thing really happened. And so I think I would have a lot of questions for the aliens about the universe and about their civilization and all this kind of stuff. But I would also really be looking for some kind of concrete evidence that I could use to prove to other people that I actually met them, that they are real, that we know that we are not alone in the universe. Because I think knowing that we're not alone in the universe would provide people with a lot of comfort. It would be scary if we are the only intelligent civilization in the entire universe, because, like, if we mess this up, then the future of life in the universe was lost with us. The future of intelligence in the universe was lost with us. So I hope there are aliens out there, and I can't wait to meet them. That'd be great. I would love to meet aliens. I mean, that's like what sci-fi is about, is partly trying to just wrap your mind around what it would be like to meet an alien civilization. Something that didn't even evolve here on planet Earth, doesn't have the same kind of society as us. What would that be like? It'd be amazing. S.A. Thigpen, what radical changes would you make if you were given the job of NASA chief? For me, the role that NASA plays, the one that I find the most exciting, is to remove risk, to de-risk spaceflight. So there are all these new technologies that are required: faster propulsion systems, new ways of providing resources in space, of gathering up material. You know, there's just a lot of stuff that is theoretically possible, but it's too risky for any commercial entity to take on and try and figure out how to do. But if those things could be figured out, then it would unlock the next step of space exploration. And, you know, I do all these interviews with the people who've won these NIAC grants, the Innovative Advanced Concept Awards from NASA. And these are the stuff that are at the very bleeding edge of what is possible, what could be done, what cool ideas are in the works now that could help us solve problems in the future. And I personally would just throw all my resources into that, into some advanced version of that, which is like, show me all of the ideas that have anything to do with spaceflight, that have anything to do with science, that are too extreme for the standard commercial industry to take on. Let's remove the risk. Let's solve the problems one at a time. Let's figure out how to make photon squeezing work. Let's figure out how to make a quantum computer work. Let's figure out how to make a nuclear rocket work. Can we make metallic hydrogen? You know, and then, oh, solved it. Great. Here you go, world. Here's the patent. Here's the technology. Commercialize it if you want, and we're going to move on. But now this is known and understood, and we've made value of it. Let's move on to the next thing. And so I think that's the role that I'm most excited about by NASA, is its ability to take the impossible and make it possible, and then move on to new impossible. They should always be working on the stuff that nobody has any idea how to do, but would be excited if that stuff could be done. And that's the role that I think NASA plays the best. And I think anytime they do anything that isn't turning the impossible into the possible is, you know, time that could be spent working on turning the impossible into the possible. So that's what I think. All right, those are all the questions that we had today. Thank you everyone who asked them in the YouTube comments, as well as everybody who showed up for the live show. Remember, we do this every Monday at 5 p.m. Pacific time. So come on by, ask your questions, ask follow-on questions, talk to the community. It's a lot of fun. And the show is like 3 times as long as the one that you're seeing here. So definitely come and check it out. And don't forget to vote. We'll count them up next week. Thanks everyone. We'll see you next week. If you want to stay on top of all of the important space news, join my weekly email newsletter. I send it out every Friday to more than 60,000 people. I write every word, there are no ads, and it's absolutely free. Subscribe at universetoday.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content. Subscribe at universetoday.com/podcast or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent. It keeps ads at a bare minimum. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Just Paul Davis, Vlad Chipolin, Jay Dennis, David Giltonen, Maud So, George, Jeremy Mattern, Jordan Young, Tim Whalen, Dave Verbeoff, Andrew Gross, and Josh Schultz, who support us at the Master of the Universe level. All your support means the universe to us.